This is the first part of the SAR ADC, which stands for the Successive Approximation Register to Digital to Analog Converter. Since the frequency is too high, around 10.1 kHz, you can't see the LED flash. And here's how the circuit works. Here's the circuit made in fault stat. As the circuit is first provided with the 5 volts, the input of the first NOT gate is a 1, and therefore its output is a 0 since it flips the input. And if the output is a 0, that means the input of the next NOT gate is also a 0 since they're chained together, and so the output is a 1. This means the clock signal is a high. And while this is happening, the first and second capacitors are both charging. However, when the second capacitor stops charging, it has to discharge, so current has to flow in the opposite direction, and the clock signal is no longer high, and the input of the first NOT gate is a 1, and the output is a 0. But the second capacitor also begins to discharge as well, so it is ground on the left side, and on the right side, it provides an input of 1 to the second NOT gate, and therefore the output is 0 since a NOT gate inverts its input and the clock signal is low. Now I'll provide a brief overview of the SAR ADC, which consists of a 7-bit R2R ladder DAC, comparator, sample and hold, analog input, 7D flip-flops, 2 shift registers, a manual and an auto mode, and finally 7 LEDs to show the digital output. An analog signal from 0 to 5 volts is supplied to this op-amp, and its output stays constant to enable the circuit so that the conversion result is correct. The shift register outputs a bit on the rising edge of each clock signal. Each output of the shift register is wired to a D flip-flop so that its output is held constant. In the first step of the SAR, all outputs of the shift register are cleared and the outputs of the D flip-flops are 1. The OR gates act as control signals for proper SAR operation, and the internal R2R DAC provides the necessary reference voltage for each bit that is wired to the comparator. Starting with the most significant bit, with a voltage reference half of the voltage supply, which is 2.5 volts in this case, if the comparison or analog signal is greater than its DAC output, then the comparator outputs a low and its corresponding D flip-flop output is a 0. Conversely, if the comparison signal is lower than the DAC voltage output, the comparator outputs a 1, also held at its corresponding D flip-flop. And each output of the D flip-flop becomes a data input for the second shift register, where its output, which are LEDs, represent the result of each comparison or show the digital value of the analog voltage. And this process is repeated for each bit.